Welcome to our poster. My name is Justin van der Hooft, and together with my colleague Florian Huber, we are presenting Spec2Vec, improved mass spectral similarity scoring through learning of structural relationships between the mass fragments in mass fragmentation spectra. The spectral similarity score is at the heart of many metabolomics analysis. It is key for library matching, but also for technologies like molecular networking, where we want to assess the structural similarity of molecules that got fragmented through their fragmentation spectra in LC-MS datasets. Today, we will introduce to you a novel way of how we can assess this spectral similarity by Spec2Vec. Florian will now explain to you how we created the Spec2Vec model.
Yeah, hello. So I would start with figure 1. And what figure 1 is, it shows a cartoon of two molecules, M1 and M2. And those create fragmentation spectra that you see below. And what we typically have is in conventional similarity scores is that we will just compare these two spectra based on their peak positions, which you can see in part B of this figure. And the problem that comes from this method is sometimes that if you have large and complex molecules, they might often have small local changes or additions to the chemical structure. And those might lead to shifts of all the, or many of these spectral peaks. And the classical method, such as the cosine score, is not able to realize that the fragmentation, the fragmented pieces of the molecule are very related, because the peak positions will be shifted and not identical anymore. So what we thought of is we use a method that comes actually from the field of natural language processing, because it is really helping with a very related problem. And this is illustrated in the sentence. So you can see likes cake with a cappuccino, and below loves to have a cookie and a coffee. And these sentences are different because although they don't share any words except for A, but the tools like Word2Vec from the field of natural language processing will still be able to figure out that those two sentences are very similar, not because they share identical words, but because those words in these sentences are very related and mean very similar things. And this is what we now try to translate into the context of mass spectra. So we adapted this method to find a way to really realize and learn from big data sets that different peaks, although they occur at different positions, are very related and share the same meaning or context. And based on these word representations, we can then build vectors, so abstract vectors for entire spectra, which is what you can see in panel D. And these vectors can then be compared to compute a similarity score. And the hope is that these vectors will much better represent actual structural similarities. And this is what we assessed in figure 2. So in figure 2, you can see a sort of benchmarking where we really try to compare quantitatively across many thousands of spectra. And what we take here is we try to compare how much does a high score regarding to, or with respect to Spec2Vec, correlate with the actual structural similarity as assessed by fingerprints. And you can see that the black curve that comes from Spec2Vec is always below these curves of cosine scores and modified cosine scores, which essentially means that on average, the high similarity from Spec2Vec correlates very well with an underlying similarity of the compounds.
Thank you, Florian. When we would zoom in into one example of two molecules, as you can see here, that are sharing the majority of their structures, but for three small subtle modifications, then we can see that the traditional cosine scorers, the cosine and the modified cosine score, are pretty low because they only share just a couple of peaks out of the total spectrum. However, Spec2Vec model was able to learn from the large data set that many of the fragments are actually very related in terms of their meaning. And thereby, to all those fragments together, add up to a pretty high Spec2Vec similarity score, which is much closer to the actual molecular similarity as here defined by the Tanimoto coefficient. So let's first go to library matching. Library matching is one of the key things in the metabolomics field to have a first look into what is actually in your sample. And to do library matching, we have to do this spectral similarity score to reference ISMB spectral data in the libraries. Over here on the y-axis, we see the true positive per query, and over here on the x-axis, we see the false positives per query. And over here, we see the different thresholds put on the Spec2Vec score and on the cosine score. And as you can see, not unsurprisingly, if we have a really strict threshold score, we have a really low number of false positives, but also a pretty low number of true positives per query. And when we slowly release this threshold to become more loose, lower, we see that the number of true positives goes up quite rapidly for Spec2Vec, whilst these false positives remain relatively low. And we can also see that it performs better across the whole board than the traditional cosine score. Of course, this is not the only thing we can do. We can also do molecular networking. As you can see here, we've created a large molecular network based on the Spec2Vec scores. And we also colored all the chemicals in there, all the metabolites, based on the chemical class as defined by classifier. And this is from this large set of nearly 13,000 unique molecules. And because we have the structures for all of them, we were able to plot these chemistries. And the bottom line here is that we see that these families created based on Spec2Vec are quite a uniform chemical class. So to wrap up, and what's also possible is that if we have one unknown query spectrum now, we can actually very quickly, within a matter of seconds, search in a large database of nearly 100,000 library spectra and find out whether there are structurally similar molecules present. So without having to submit the parent mass, this is really based on the fragments and the losses only. And this is really going to be also a very nice application of this Spec2Vec model. So with that, I would like to round up this poster presentation. I want to thank you for your attention.